Hey guys, welcome back. So we're going to start looking at some of our transformations of quadratic functions. Now, there is a lot to kind of go over and absorb today, so make sure you're taking really good notes, be as detailed as possible. Pause this throughout as you go so you can make sure you get all the information on the slides and add to what I have on here, okay? The first thing I want you to do, and I actually want you to please make sure you do this because it is important and it leads into what we're doing. I want you to write down the functions over here in your notes. Okay, so write those down. After you write them down, go ahead and switch over to open up Desmos, either the calculator or just the Desmos.com calculator, and just graph each one of these functions. And what I want you to do is just right next to the function, I want you to put wherever that vertex is located. Okay, wherever the location is for each one. Some of them are going to be obvious to you. Some of them might surprise you. So I want you to just actually go through this exercise. And then I want you to analyze your results. I want you to compare where that vertex is with the actual function that created the graph. Okay? Just the vertex. Don't even pay attention to anything else. Just notate where that vertex is. Some of the results might surprise you. All right? So go ahead and pause here and go through that first. Okay, so if you graphed these correctly, right, you should end up having a vertex of 0, 4 for number 1, 0, negative 3 for number 2, negative 2, 0 for this one. Number 4 should have ended up being 4, comma 0. And let's see, this one would be a negative 3, negative 2. And then finally, a 1, comma 5. So hopefully you were able to kind of analyze your results and see some similarities, some differences. If you spotted them, great. Okay, it means you're critically thinking, which is good. The adding a number or subtracting here should have been fairly obvious because of all the function work we've done in the past. It tends to shift things. Oops. And now, you might have been surprised from some of the results when we had a plus or minus inside the parentheses before they got squared. And that's kind of what we're going to focus on today. So the lesson is transforming quadratic functions. Okay, so we're going to start manipulating the parameters and seeing how they change the graph. All right, so the first thing we're going to deal with is the easiest one. This is the one we've been doing all year. Vertical translations, okay? So when it shifts up or down, it always is dictated by that constant, okay? And we're just going to use the variable k or the parameter k in place of any other letter. Just k is going to be our constant. And you should have noticed from graphing these and notating them that when you added, when you added a constant, right? This shifted the graph upwards in the positive direction. And when you subtracted a constant, it shifted it down in the negative direction. Okay, this shouldn't have been a surprise. We've been doing this all year. But just to kind of reinforce the idea, let's go ahead and graph this parent function alongside a new function, g of x equals x squared plus 2. So let's just take a look here. So we're going to plug in, let's see, negative 3, negative 2, negative 1, 0, 1, 2, and 3. So when I plug it into the parent function, like we did last week, we already know that it's going to be 9, 4, 1, 0, and then, of course, it's going to mirror, right, because of the axis of symmetry, so 1, 4, and 9. Now, when we start to plug in our values, well, actually, let me stop there for a second. Let's graph this real fast because we're going to compare it. So 0, 0, 1, 1, 2, 4, 3, 9, and then the mirrored points on the other side. All right, and when I sketch this, I just want to be as smooth as possible. No sharp angles. These are not absolute value. Okay, so it's not a V, it's a U or a parabola. All right, and let's compare it to this other function. So if we were to, this one's kind of easy because all we have to do is add 2 to our results from the parent function, right? So we're just going to add 2 to each one of these. So this would be 11, which no longer, well, it does fit on the graph. We can do that. 4 plus 2 is 6. 1 plus 2 is 3. 2, and then the mirror points, 3, 6, 11. Okay, so let's graph this, and you'll see that, all right, well, if we have 0, 2, I like to start with the vertex. So 0, 2. 1, comma 3. 2 is going to be 6. And 3 is 11. And then, of course, our mirror points, so here, here, and here. So you can see how the shape doesn't change. That was not very smooth. The shape doesn't change, but the entire graph is shifted upwards by 2 units as determined by that constant of 2, right? So if we had subtracted 2, the whole thing would be shifted down 2. So vertical translations we've been working with. So let's talk about, oh, I forgot about this. What is the equation for the axis of symmetry? So remember, our axis of symmetry is this imaginary vertical line that passes through the vertex. And make a note for yourself, when I ask you this in the future, I do want the actual equation of that line. So in this case, because it's vertical, it's an x equals equation. So x equals 0. Another question I'm going to be asking you in the future is, would you consider this point, this vertex, a minimum or maximum value? So just keep in mind that these two parabolas are pointing upwards because the parabola is opening upwards. So these are the lowest points on the graph. So these would be considered minimums, or just min. You can abbreviate. Okay, so let's talk about horizontal translations. And this is the thing that might have surprised you when you did the graph on the Desmos. All right, so we do know that we have another parameter here. In this case, we're going to use h for horizontal, okay, or horizontal changes. And you'll notice that these are inside a set of parentheses that is now being squared, right? And so here's the thing with horizontal translation. If I'm adding an h value, which would be positive, we're actually going to be shifting the graph left in the negative direction. And if we subtract an h, it's actually going to be shifting it horizontally to the right in the positive direction, which is kind of unusual, kind of unique. But let's take a look at an example and see how it compares to that parent function. So let me graph that parent function again real quick. All right, and then the negatives. All right, so here's my parent function. As always, vertex is at 0, 0. And let's compare it to x minus 1 squared. Okay, so now keep in mind, order of operations, we're going to be doing, let's see, negative 3 minus 1, and then squaring it, right? So negative 3 minus 1 is negative 4. Negative 4 squared is 16. Then we're going to plug in a negative 2. So negative 2 minus 1 squared would be negative 3 squared, which would give us 9. Negative 1 minus 1 would give us a 2 squared, negative 2 squared, so 4. And now this is the point I'm really interested in. This is my vertex. So the vertex is going to be 0 minus 1 squared. And you'll see, okay, because I'm squaring it, that becomes a positive. So this is actually going to shift it to the right in the positive direction, even though it's a minus 1. And then, of course, we start seeing a repeat or a mirroring from the axis of symmetry. So 1 minus 1 is going to be, it's going to be 0 squared, so 0. This is going to be 2 minus 1 squared, So 1 squared would be 1, and then 3 minus 1 squared would give me 4. So you should notice something here, that my mirroring doesn't happen at the same location. So what actually happened was, what I thought was going to be the vertex, because it was originally the vertex on the parent function, is no longer my vertex, right? My vertex is my middle point. So you'll see a mirroring here and here, which means my vertex is no longer 0, 1. My vertex is 1, 0. So when I graph that, see my vertex moved or shifted horizontally to the right. So my second point would be 2, 1, 3, 4, and then I don't have the mirror point, but I know because this is a 9, you should be able to determine, okay, if it's 4, it's also going to be 9. So 4, 9, and then the other direction. So 0, 1, -1, 4, and -2, 9. Lost my place. Okay, so when we graph this, we see that the whole thing, that wasn't very good, has been shifted to the right by 1 unit, right, to the right, which is the opposite of what you might think because it's a -1. So keep in mind that little fact. Okay, if we're subtracting an h value, it's actually moving it to the right. If we're adding it, it's going to shift it to the left. So what is the equation for the axis of symmetry now? Well, now the vertex now passes through, the axis of symmetry now passes through the vertex at 1, 0. So if my vertex is at 1, 0, that means my axis of symmetry is x equals 1. And again, because this opens upward, this is still a minimum value, so that doesn't change. All right, which is kind of interesting. Now this brings us to what's called vertex form. Vertex form is great for finding the vertex. Okay, it's also kind of the starting point when you're trying to build a function from a graph, which we'll get to in a minute. All right, so here's the vertex form with all of the parameters we could possibly add to it. We have our a value, which you guys should remember determines the shape and the direction, right? Smaller the value, the more compression. Larger the value, the more stretch. If it's a negative value, it also causes reflection. That was something we talked about last week. Our h value is always where our axis of symmetry is located. All right, and then of course we can describe the vertex using h, k, but we have to keep in mind that opposite value thing. So if we have a minus here, it's actually a positive hk. If it's a plus h, it's actually going to be a minus h, k. All right, so let's see how well you're understanding this. Here's all the parameters in one function. All right, so pause this, graph it, and you should be able to tell me a couple of different things by the time you're done. All right, so I'm going to choose some, well, actually these points are already chosen for you. So -3, if we plug in -3, I'm just going to do this mentally as we go. So -3 minus 1 would be -2. -2 squared would be 4. 4 times -3 is -12. -12 minus 2 is -14. So this is going to be a -14. Let's see, -2. -2 minus 1 would be -1, which would be 1 if you squared it. So -3 minus 2 is -5. And then -1 plus 1 is 0, which would give us 0. Times -3 is also 0, which gives me -2. Plugging in a 0 gives me a 1. 1 squared is 1 times -3. So I'm back to -5. So this is my axis, or sorry, my vertex here. right, is -1, -2. And then, of course, this should be a 14. So if you kind of jumped ahead mentally and said, well, I already know from the pattern that my vertex is going to be the opposite of h, right? This is h, and the same as k. So it's the opposite of h, but the same as k. That means my vertex is going to be located at -1, -2, which is exactly what we determined from using the table, right? So the next thing you should be able to answer is it a minimum or maximum? Well, I know my a value is a -3. So before I even graph it, I should be able to determine whether it's a minimum or maximum. But let's go ahead and graph this just to see. So -1, -2 is my vertex, 0, -5, 1, -14, and then the mirror points would be -2, -5, and -3, -14. So let's see if I can sketch this real quick. All right, so you should, at this point, excuse me, be able to determine a couple of different things, right? Just from the function itself without having to make a table, without having to make a graph, right? So is it a minimum or maximum? Well, it's at the top of the graph now. So this is actually a maximum or a max. What's the axis of symmetry? Well, all I care about for the axis of symmetry is what is the x value of the vertex. X value is -1, so the axis of symmetry is going to be x equals -1. And what transformations does the a value, remember this is our a, what does that tell us about the graph even before we graph it? Well, we know it's negative, so it's a reflection. And we know it's a number bigger than -1, so this is actually going to be a stretch. Okay, so those are some of the things I'm going to be expecting you to know or be able to determine without the graph, with just the function itself. Okay, so how do each of those parameters, a, h, and k, how do they describe the graph without graphing it? All right, so let's see if you can do this. So here's a new function, okay, g of x equals 2 times x minus 1 squared minus 7. Without graphing it, without making a table, pause this, see if you can write down all those same pieces of information that we just talked about. Okay, so what's the vertex? What is the axis of symmetry? Is it a minimum or a maximum? And what are the transformations other than those? Okay, so pause this, fill that information in, see if you can do it without the graph. All right, so our vertex is always determined by h and k. So hopefully you remembered it's the opposite of h, but the same as k. So my vertex is going to be at 1, -7. My axis of symmetry is the same as the x of the vertex. So x equals 1. It's going to pass right through 1. My a value is a positive, which means my parabola opens upwards. So this is a minimum value. My vertex is the minimum. And what other transformations? Well, I know my a is positive, so it's not reflected, but it is a 2, which is bigger than 1. So this is actually going to be a stretch. Okay? It's also been shifted horizontally to the right. Because it's a -1, so it's been shifted +1. And it's been shifted vertically down 7 units. And I probably should have indicated shifted to the right 1 unit. Okay, so make sure you're able to kind of describe all those transformations just by looking at the function itself. Okay, so let's let's go back to our standard form, and how do all these two forms, vertex form and standard form, how do they link together? All right. So the first thing is standard form in the quadratic is y equals ax squared plus bx plus c. This could also be f of x, right? We know that means the same thing. So one is function notation, one is algebraic notation. So ax squared plus bx plus c. A couple of notes here. A, b, and c have to be real numbers, which is all we really deal with. And your a cannot be equal to 0. So a question I might ask you, hint, hint, on a future exam, is why can't a equal 0? So think about that. Why is a not allowed to be 0? Well, if a was 0, this whole term would be 0. So what are you left with? Well, you're left with y equals bx plus c, which is a linear or straight line function. Okay, so if it's not 0, or if it is 0, it's not a quadratic, it's a linear function. All right, so when we're in standard form, let me get rid of my markings here because I need this. All right, when we're in standard form, we can actually find the axis of symmetry using the expression negative b over 2 times a. That's actually going to give us the x value of the vertex. Okay, this guy right here. So if I keep in mind a, b, and c and where they are in relation, as long as it's in standard form, I can determine what the axis of symmetry is. Well, how does that help you? Well, it gives you the x location of that vertex. Great. Well, how do we figure out the y of the vertex? Hopefully you know enough by now that you could have answered this already. We're going to plug it in to the function. Now, this looks like a mess. This is just like the actual algebra behind it. So we're going to substitute that x value in to the equation to get the y. So we're just substituting the x to find the y. And that's going to give us our vertex. All right, so let's look at an example. So if I ask you to find the vertex of this function, the first thing you have to do is rewrite it in standard form, which means we need to get it as y equals with everything else on the right-hand side. So y equals, I'm going to add 2x squared. So 2x squared plus 8x plus 7. So just rearranging some things to make sure it's in standard form. Okay, my axis of symmetry, we're going to find it using negative b over 2 times a, which is pretty easy to do because my b is my b is 8, so negative 8. And we're going to divide it by 2 times the a value, so 2 times 2. So negative 8 divided by 4 is negative 2. So I know that my axis of symmetry is x equals negative 2. So that's my x value of the vertex. The next thing I'm going to do to find the vertex is substitute negative 2 in for my x's. So that means we're going to calculate the y at 2 times negative 2 squared plus 8 times negative 2 plus 7. So let's simplify this out using order of operations. So 2 times 4 minus 16 plus 7. That's going to give us 8 minus 16 plus 7. So negative 8 plus 7. Sorry, this is all y equals, y equals, y equals. So my y equals, oh, I ran out of screen space. My y equals negative 1. So my vertex is located at negative 2, comma, negative 1. Okay, so this is, I know there's a lot of formulas in this unit. That's just the nature of the beast. So there is some, you probably want to create a separate piece of paper that's got all of the expressions and formulas and functions that you're going to need for this unit. Okay, because I know they're easy to get mixed up. When you're completing the square, you've got b over 2 squared, you've got b squared over 4a, and now you've got negative b over 2a. There's a lot to absorb, so make sure you're keeping track of these on a separate piece of paper. All right, the other thing we're going to have to do in this lesson is convert from vertex form into standard form. And this is going to help us build our functions from a scenario, which is kind of where we're headed with this. All right. So if I gave you this particular equation, y equals 4 times x minus 6 squared plus 3, and I asked you to put it into standard form, because currently it's in vertex form, right? Currently it's in vertex form. You're going to follow these steps. You're going to expand it, you're going to multiply it, and then you're going to simplify it. So once again, it becomes useful to know that pattern of perfect square trinomials, right? It comes back to us. So remembering that a minus b squared multiplies out to a squared minus 2ab plus b squared. So I'm referring to this part right here, x minus 6 squared. So 4 times x minus 6 squared is going to give us an x squared minus 2 times a times b is going to be minus 12x, and then b squared is just 36. Okay, so that's what we mean by expand. Then we're going to multiply 4 times all that stuff, so 4x squared minus 48x, and 36 times 4 is 144. And then we're going to add 3. Remember, this is y equals. So we're going to add 3 to this, so this is what I mean by simplify. So my standard form of this same equation is 4x squared minus 48x plus 147. Okay, so that's expanded into standard form. All right, so this brings us to my challenge question. I'm actually not going to give you the solution to this. I'm going to ask you to write it down. You're free to work with somebody else in the class. If you guys want to FaceTime and talk about it, just make sure both of your names or 3 of your names or however many is working on it is on your name, or sorry, is on the paper. I want you to answer this question, both parts. There's 2 parts. And email it to me, okay? If you manage to get the whole thing correct, it's going to be bonus for the test coming up. All right, so here's the scenario. House painter standing on a ladder, 25 feet up, drops his paintbrush, whoops, falls to the ground, as that's how gravity works. Use the graph to write an equation in standard form for this situation. I will give you one small hint. Don't try writing it in standard form until you create it in vertex form first. Okay? Once you've done that, the second half of this challenge is to figure out, so solve, the approximate amount of time in seconds, rounded to the hundredths place, that it takes for it to hit the ground. So where exactly is that in time? Obviously it's between 1 and 2 seconds, but what is it exactly? All right, answer that question, email it to me. Good luck, guys.